yeah, I've become a much bigger fan of doing these videos because, well, then if people can't make it in, they can still watch. So, okay, so what I plan to do for today is I'm going to do this review kind of in two parts. The first part is going to be a summary. I'm going to go through all of the important topics, okay, that I think you need to be studying and know about. Just make sure we get everything back in your head again. And then I have several example problems. Okay, my guess, just based looking at all the stuff I have, is it's probably a good 2 hours anyway of stuff. If it's going a lot longer than that, feel free to take off if you have to, and I don't have to stay the whole time, or I can try and curtail things a little bit too. But I do have quite a bit of stuff here to go over, so this will be hopefully helpful. And then I have I'll be here tonight for office hours. I think my normal hours from 8 to midnight, so after the end of the review, I'll take a little break and then come back if you want to talk tonight about anything. And then I'll be around, of course, a lot on Monday, Tuesday, and Wednesday leading up to the test. So that's kind of where we're at. So let me start with an overview of some of the key topics that you guys need to be comfortable with, okay? So I'll start over here. Overview. Of course, the review packet talks about exactly which sections you need to know and you know, the main things to be able to do. But I just want to highlight some of them here. Sort of where the exam begins is in section 2.2. We learned about the coordinate vector for a vector. So let me write that down. Coordinate vector. So this is kind of the first topic. Coordinate vector. And this is always relative to a basis, which I'll denote as beta. So we have a basis. And actually, it's an ordered basis. I don't always write the word ordered, but we almost always are referring to an ordered basis at this point in the course. Even when we do diagonalization, eigenvalues and eigenvectors, we need to keep track of the order of the basis in terms of how we're listing the columns of Q and the lambdas on the diagonal of D. So this is very important. This basis is really ordered. Keep track of the order. You'll see right away on the sample test, I think the very first question, I give you a basis for P2 of R, which is like x and then 1 and then x squared. I kind of put it in a strange order just to make sure everybody was on their toes about the order of the basis. So that's something you should be comfortable with. But anyway, if I give you a vector v in the vector space V, it can be written uniquely as V equals A1 V1 plus A2 V2 plus dot 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 plus AN VN. So maybe I should come back up here to the first line again. The ordered basis beta is V1 V2 up to Vn. Okay, so we'll say that this is an n-dimensional vector space. We put down an ordered basis, beta. And so every vector can be written in this sort of a format. So then the coordinate vector, if you guys remember, the coordinate vector of v relative to beta, okay, is literally just the column consisting of the scalars of those linear combinations. Okay? This should be something that's you know, not too difficult to calculate, right? If I give you a vector, you have to figure out how to express it in terms of the basis uniquely. That might involve solving a system of equations or something like that. It's not a theoretically difficult concept, right? It might be a little difficult computationally. Maybe you have issues, you have to do some EROs or something like that. And sure, anybody might make a mistake when they're writing this down. But as long as you're doing the right process, you're going to get most of the points on a problem on the test, especially on a test, most of the points for doing it by the right method. And if you make a mistake on an ERO simplification, you know, don't dwell on it too much. That's not really the most important thing at this point. So this is a very simple theoretical concept. All right? Everybody okay with that? Coordinate vector. And then kind of going along with that, the second main topic kind of in this section is the matrix representation of a transformation. So let me write that down. Matrix representation matrix representation of a transformation T that goes from V to W. So we have two vector spaces, V and W, and we have to establish bases on these vector spaces. So let me just use beta and gamma for V and W. Okay, and beta might have N elements in it, and gamma might have M elements in it. So the size of beta is N, and the size of gamma is M. They don't have to be the same. Okay, but given that information, then what we can do is write down an M by N matrix, right? So this gives us the matrix representation. So the way we write that is T is in brackets from beta to gamma. Okay, from beta to gamma, and all that is it's the matrix. Okay, this is something everybody needs to be able to just do cold, which is write out how this matrix looks. What do? Well, you take each basis vector from beta, you transform it. So you're going to take the first basis vector, you're going to transform it, and then you're going to write its coordinate vector relative to the new basis gamma, right? Okay, and then you do the same thing. I'm going to get this out of the way here. You do the same thing in the second slot, T of V2 with respect to gamma, and then dot, 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 all the way up to T of Vn with respect to gamma. So you just build that very large matrix in a column by column fashion. Okay, and then there's a relationship between coordinate vectors and matrix representations. So let me just write that down. So the relationship of 1 and 2, the relationship between those things is that if I take a vector V in the vector space and I want to transform it under some transformation from V to W, then the way that we can do that by using coordinate vectors and matrix representations, okay, the way I can do it is, and this is a diagram that should be in your mind as well, is I can first find the coordinate vector of V with respect to beta. I can then apply the matrix representation T from beta to gamma. I can multiply the coordinate vector by that, right? So in other words, I'm going to take the matrix from beta to gamma of T times the coordinate vector of beta, of V with respect to beta. Notice these two have to be the same, okay? And what this actually gives you is T of V with respect to gamma. This equation right here, this is theorem 2.14, early on in chapter 2 of the book, okay? And of course, once you have the coordinate vector of T of V, then you actually also have what T of V is, because you know what all the scalars are. You know how to write T of V as a linear combination of the basis gamma, right? So you just have to go back then and write down what T of V is. So that's a way of computing T of V by using the matrix representation. Why would you want to do that? Well, maybe I don't give you a direct formula here. Maybe I only give you the matrix, right? Then you would need to kind of think of it in this format. Okay. Interrupt me with questions as we're going along here if there are any issues. Okay. Let's see. One of the important things about the matrix representation is that if we ask questions about T, transformation from V to W, we can often answer them by answering the same question about the matrix representation. So to answer questions about T, right, we can often appeal to the matrix representation of T. Okay. Let me give you some examples of that. So examples. Here's a question about T. Is T invertible? Well, a matrix representation of T and ask if that matrix is invertible. Well, one thing about the matrix to be invertible, it has to be a square matrix. Well, if it's going to be a square matrix, then beta and gamma have to be the same size. That means the dimension of V and W have to be the same. So you see, and that's not a sufficient condition, but that is a necessary condition for T to be invertible. But really, you're just looking at this matrix. It needs to be a square size, and then it needs to be invertible. And it doesn't matter what beta and gamma you chose to work with, right? Any choice of bases here will give you the same result. So everybody remember that? That's because any two matrix representations of a linear transformation are always similar. Similar matrices have a lot of common features. They have the same determinant, for example. So if the determinant is non-zero for one matrix representation, then it's also non-zero for any other, right? That will be a consistent fact for all possible matrix representations. So you just pick one. You can appeal to any choice here. Usually we choose easy basic, choose beta and gamma to be very simple. Right? That's what you'd normally want to do. But in theory, there's no right or wrong basis to use. And that's usually the case. There usually isn't a right or wrong basis to use. Another question that could be answered by using the matrix representation would be, is T diagonal? Diagonalizable, right? Is it diagonalizable? Another one would be, what is the determinant of T? Okay. Another one is, what are the eigenvalues? What are the e-values of T? Okay. Another one would be, what is the Jordan canonical form of T? That really means of any matrix representation of T. So these are the sorts of questions. To answer these questions, really to answer these questions, you should be thinking about converting to a matrix. It's not just that you can do that, it's that you should do that. Right? If I say, what are the eigenvalues of a transformation? Everybody should be thinking, step one is write down a matrix representation. Okay. And that's really true. It's for example, the invertible question, you could try to answer that without using a matrix. Like you could try to see, well, is there a way to put down a formula for T inverse where it's such that T composed with T inverse in both directions is the identity. But that's just not the easiest way to do it, right? The easiest way to do it is to actually use the matrix. And then if I ask you, okay, so let's suppose T is invertible, and then I ask you, okay, it's invertible, find the inverse. Well, then you have another thing you can use. So let me just follow up here on this first question. You remember that you can actually find T inverse by finding its matrix representation first, right? So T inverse would go from gamma back to beta, and the formula for that is take the matrix of T from beta to gamma and invert it. Okay? So if you have already found this matrix, then you just simply have to invert it. I say simply. Maybe not always that simple. Does everybody know the formula for the inverse of a 2 by 2? This is worth memorizing. It's just right, 1 over the determinant of the matrix times the matrix. Basically, you swap the A and the D and you put minus signs on the B and the C. That really is worth committing to memory, not just for this class, but sort of forever. It comes up a lot. I'm probably not going to ask you on the test to invert anything larger than that. I might ask you some question about the inverse. For example, maybe I'll tell you, oh, if the eigenvalues of T are 2, 3, and 4, and the matrix is invertible, then what could you tell me about the eigenvalues of T inverse? And I would expect you to remember that homework problem where you prove that if lambda is an eigenvalue of t, then 1 over lambda was an eigenvalue of t inverse. So if t has eigenvalues 2, 3, and 4, then the eigenvalues of t inverse would be 1/2, 1/3, and 1/4. You can answer that without ever actually finding t inverse, you see. So you don't actually have to do a hard inverse calculation, but you can answer that kind of question. Does that make sense? That's the sort of thing I'd be more likely to want you to be able to do. Or if I want you to work with a bigger matrix, I'll just give you the inverse or something. I'll just tell you the formula for it. Try to help you out a little bit. Okay, are we doing okay so far? All right. This matrix representation thing is so powerful that we actually, if you remember, we actually were able to develop sort of an isomorphism of sorts. So this is kind of the third point. You guys remember the script L of VW? This was the notation that we set up. This is just the set of all transformations T from V to W. These are the linear, these are all of the linear transformations from V to W. Okay, at first glance, that is just a set. It's just a collection. It's just a set of linear transformations. But then what we saw is that we can actually add two transformations together, and we can take a transformation and scalar multiply it by something. And then with those operations in place, all of the axioms for a vector space turn out to hold. So this thing, as we saw, this is actually a vector space. And it's, as a vector space, isomorphic. Do you guys remember this part? Isomorphic. It's isomorphic, so let's assume that this is n-dimensional and this is m-dimensional. Does anybody remember what it's isomorphic to? Say again?
Onto n.
But what other vector spaces is this one isomorphic to?
All linear combinations?
Well, we can take transformations and form all of the linear combinations. That's part of what's in this set, right? Okay. No, the answer I'm looking for, so if I take a transformation and I want to associate it with something, what we associate it with is the m by n matrices. Right? Do you guys remember that? Basically, what's the isomorphism? If I want to call it phi, phi of a transformation T is just literally the matrix representation of T from beta to gamma. So you fix these bases, beta and gamma for V and W, then you can take a transformation and associate a matrix with it. Okay? And this function phi respects addition. It respects scalar multiplication. I forget which theorem number that is, but there was a theorem. I just stated it. I didn't really prove it because it's kind of not that interesting to prove. It's fairly straightforward to see that, for example, phi of T1 plus T2 would just be phi of T1 plus phi of T2. So in other words, the matrix representation of T1 plus T2 from beta to gamma is just the matrix representation of T1 plus the matrix representation of T2. Right? So, so phi respects addition. It also respects scalar multiplication. It's also one-to-one and onto. For example, to see that it's onto, if I take a random matrix over here, how do you show something's onto? You pick something in the codomain, and you find a pre-image for it. Well, we happen to have a pre-image for this, which is L sub A, if you remember. L sub A is the linear transformation, which is left multiplication by the matrix capital A. And when I tell you that that's the pre-image, the reason that that is the pre-image is because if you do L sub A and you build a matrix representation of it with respect to beta to gamma, now beta and gamma in this case are going to be the standard basis vectors on let's see, this is, so A is an m by n matrix, right? So this is a standard these are the, so this is m by n. So, right, beta has m elements in it and gamma has n elements in it. So, so this just ends up equaling that. Okay, so anyway, so it's on to. And then it's also pretty straightforward to see that it's 1-to-1. So it's actually an isomorphism. Okay, so it's an isomorphism. Okay. So far, so good? Questions so far? Okay, great. Getting through my overview here. The next thing that should be on everybody's practice before Wednesday list would be composition. You have to go back to the homework and review some of these that you did quite a few weeks ago now. But the basic setup here is that if I have a transformation T that goes from V to W, and then another transformation U that goes from W to Z, right? Then we, of course, can compose those two together. We can compose these together and get a single transformation here. Let's say I have bases alpha, beta, and gamma for V, W, and Z, respectively. Then what we're going to get is a composition which is U composed with T, and this will be going directly from V to Z. And each one of these transformations, T, U, and U composed with T, each one of those has a matrix representation relative to the appropriate bases. So the theorem that you want to know, which is theorem 2.11, tells us that the matrix representation of U composed with T, now this would go from, so U composed with T is going from V to Z, so that means we're going from alpha to gamma, right? That is equal to, does everybody remember? And that will go from beta to gamma, right? Right, from alpha to beta, right? So there's the, and the betas have to be the same. Those two have to be the same. You sort of cross them off and you're going directly from alpha to gamma at that point. Okay, so this is a nice thing to know. All right. We actually proved that one in class. I wouldn't ask you to prove this in class. It was very technical, so you won't be asked to prove that on the test, but you should definitely know what that theorem is about. Okay, helps you to work with the composition of two transformations. Okay. All right. Let's see. What else do we want to have everybody review? Invertible linear transformations. Invertible linear transformations. This would be the next thing. Okay, so T from V to W is invertible. Of course, by definition, that just means that there exists another transformation U that goes from W back to V with U composed with T equaling the identity of V and T composed with U equaling the identity of W. So those two compositions have to basically end up canceling out, right? The composition of those two transformations. A lot of times, though, we don't want to check invertibility this way, because checking for an invertible transformation this way means we're looking for this existential U, right? We don't know how to find it, though. A better way to think about T being invertible is just the basic, back to Math 280, just means that it's 1-to-1 and onto. Okay, so T is 1-to-1 and onto let me just remind you exactly what that meant. Can anybody rephrase 1-to-1 for me? If T is 1-to-1, what's another way of saying that? Exactly. The null space of T is 0. And T being onto, do we know how to rephrase that one?
The range of T is W.
Exactly. The range of T is all of W. So these notations, the null space of a transformation and the range of a transformation, are important to know. That chapter 3 that I asked you to kind of read over spring break and you just did that one assignment on has a lot of this basic stuff on null spaces and ranges of transformation. But this is just another way of saying 1-to-1 and onto. Okay? And of course that's just another way of saying that T is an isomorphism. So I think when you look at the sample test, you'll see some examples. I write down a proposed T from V to W, and I say, is it an isomorphism, right? Now, all I really just mean is it invertible, okay? Now, notice on this last step, I'm only doing a forward arrow. But in order to have an isomorphism, what do you know about the dimensions of the two spaces V and W? Exactly. They have to be the same. So if I give you two spaces that have different dimensions, then you should know immediately that it is not an isomorphism. Okay? And I would expect you to draw that conclusion quickly. Don't spend a lot of time on it, because I'm figuring that into how much time the test is going to take. Right? So if I give you two spaces that are different dimensions, you should be done in literally 5 seconds. Okay. And then final thing here is that this is theorem 2.19, is that two spaces V and W are isomorphic if and only if they have the same dimension. So they have to have the same dimension for that to be true. Now, just because they have the same dimension, though, doesn't mean that every possible transformation will be an isomorphism. Right? I can have two spaces that are the same dimension, and I can give you a transformation that's not 1-to-1 and onto. But what this is saying is that there exists some transformation that is 1-to-1 and onto. But I might give you one that doesn't work, right? So you have to be a little careful about that. Okay. So far, so good? Everybody doing all right? I'm trying to hit some of the highlights. This is all from chapter 2 so far. And there's 1 or 2 more points I want to make here about chapter 2 before we move on. So number 6, I think we're on. Number 6. Are there any questions so far? Everybody all right? Questions will start coming when we get to the problems, I guess. Okay, so change of coordinates. So this is where you have 2 different bases for a vector space. Call them maybe beta and beta prime. And of course, you can talk about coordinate vector of V with respect to beta, and you can talk about the coordinate vector with respect to beta prime. And what is the connection? How can I go from one to the other? Well, the way you do it is the change of coordinates matrix. So that's what this is about. Let me remind you of the setup of this. Basically, so we have beta and we have beta prime. These are my 2 bases for V. So beta and beta prime, these are bases for some vector space V that we're starting with. And the idea is that we can convert sort of from one to the other, or back again,